processes, because I will talk about earthquake-induced landslides. So in this case, the same process, the earthquake is both a player in the tectonic deformation, but also in the erosion of the landscape. And so it's a fairly important problem, both in terms of mountain building, but also sedimentary budget and natural hazard. So a very simple question is what will be the total volume of all the landslide produced by an earthquake? So it has been investigated already in the 90s, and people observed that there was a almost linear relation between the total volume and the seismic moment. So the bigger the earthquake, the more landslide. This seems intuitive. So this was the fit here in the dashed line. But we have updated and compiled a much more significant database of earthquake-induced landslide, about 35 earthquakes of very different, with a large diversity. And you quite see that the fit doesn't really hold anymore. And if you fit another curve, it would be strongly nonlinear, but with a lot of scatter. So we wanted to have a better understanding of the process and to see how other parameters are important in this data. So to try to model this, we started from recent work from Meunier and collaborators that say that the landslide density, so the amount of landslide per unit area, is relating to the shaking or the peak ground acceleration. So this was observed in the Chichi epicentral area, North region, over earthquakes. And so what you see is that the landslide pattern, so the distribution of landslide in the epicentral area, follows a wave attenuation pattern. As you go away from the epicenter, you have less landslide. And so from this, you could say that there's a total volume that we can expect with a model where the landslide occurs because of the shaking. So it will be the spatial integral of this density of landslide here. And this density of landslide actually is the integral during the earthquake rupture time of a term here that depends on the waves and that attenuate with distance. So I skip you a little bit through, I will not show all the math, but if we go to the final expression that we developed, so you have the predicted total volume that will depend on the sensitivity term. So it says how much landslide you could have in an area for a given shaking or acceleration. So it depends on the rock strength, on the geometry of the parameters. Then you have actually a rupture time component, so that depends on the length of the fault over the rupture speed of the earthquake. And the length is very really well known. It's scaling as a power law of the moment. And then there is this term that mainly depends on the acceleration, so or the wave amplitude produced by the earthquake. This is A. And we also know it's from seismological engineering that it is scaling with the moment. And this wave amplitude, of course, is modulated by the depth of the earthquake, so R0, and the critical acceleration, because this is a threshold process, so if you have too small acceleration, you just have nothing. And then you have a geometrical term that says that this sensitivity term, that is most under constraint, if it's 0, of course, you have no landslide in a given cell. So and we know that if the slope is 0, so if you have very flat area, you will have no landslide, whatever the shaking. So this accounts for that. And so if we compare our prediction to the data I've shown you before, this big compilation, we found that actually, if we have the estimated volume divided by the predicted volume, so it's residual, it is not constant, and it is strongly dependent on the model slope of the epicentral area. So that is the most common slope of the DEM. So the steeper the area, the more landslide you produce. And this mathematically comes to the fact that our sensitivity term is an exponential function of this model slope. So it's a semi-log plot that you see here with most of the data. And this is a remaining sensitivity that is non-dependent on geometry. And it seems to be mainly dependent on what we have still ignored, that is the lithology. So this goes to a full equation here. And there is only this parameter, so that is a lithological sensitivity that is fit, and also this constant that scales the slope dependency. But all the rest is data or constant. And you see, when you're looking at the final residual, that we predict fairly well most of the total landslide volume for most of the earthquakes on almost all the seismic moment range. There is about 25 well-predicted events, much better than with the empirical fit based on the moment. And more interestingly, we have explicited what caused some events to be outlier. For example, this event in Italy, they produced a really small number of landslide. And so with our model, we would say, oh, probably it's lithology that is stronger. And indeed, these are dominated by really strong limestone cliffs that produce only a few small rockfalls. So this was a flavor of this part about the spatial effect and the instantaneous effect of the earthquake. Another thing we have looked at is what happens in terms of a long-term effect of the earthquake on the hill slope. So to look at that, we monitor the evolution of the landslide rate in Papua New Guinea. So we mapped landslide with satellite images, and between two images, you can compute the total volume of all the landslide, and divided by the time, you have a rate. And here, black dots are shallow seismic events with their seismic moment here, and in red, you have a precipitation curve. And what you see when you have a large earthquake, Finisterre 96.9, of course, you have a very large increase of the seismic rate. But then in the 6 months after and in 2 years after, you have still more than 10 times more landslide than before. And this cannot be accounted by the aftershock that decay really fast. It cannot be accounted neither by a large storm. So we have more landslide, but we have the same forcing. It seems like the earthquake has changed the response of the landscape. And so clearly then, after this elevated landslide rate, you go back to something approximately equal to the pre-earthquake rate. And we found that actually in other areas in Japan for 2 other intermediate earthquakes, but also in the Chichi area, so the large Chichi earthquake in 1999. So here, again, same type of plot. We have the hydrograph, so the river discharge in the catchment near the epicentral area. And in green, you have the total landslide volume, so it's not normalized by the time. And you can see that it varies a lot. So the landslide volume produced in a couple of months, sometime even less than that, seems to vary by at least 2 orders of magnitude. And you see the high points are clearly related to typhoon. So this is Typhoon Hub, very strong flood. This is Typhoon Taraji, very strong flood. And you have other events like this. And oppositely, in the winter time, you have low flow and low precipitation, and you have a very small amount of landslide that is produced. So we can correlate this and normalize for the climatic forcing that is obviously very strong here. So to do that, we remove the base flow part of the hydrograph. So we filtered out the low frequency variation of the discharge and only kept the very short time variation that is a proxy for precipitation. And when we do that, we have what I call a run of discharge, or that is a proxy for precipitation. And it's strongly correlated to the landslide volume in the given interval. So you see here the open circles are the data for the pre-Chichi landsliding. And it's clearly correlating, so a very good correlation coefficient, and it's, again, an exponential relationship. And then what you see is that for the event just after Chichi that are color-coded from red to blue, you have a very large increase of the total landslide produced for a given rain, and then it progressively goes back to something that looked like the pre-earthquake rate. And for some control, in 2013, so many years after, we still have similar relationship. So if we use this empirical climate normalization, and we divide every data point here by the predicted volume according to this relationship, we get this. So here you have, of course, something that is very close of a constant average rate for a given rain. And then you have the earthquake that is not normalized, it's not related to rain. But then in the following winter, you clearly see that it's much above what you should have had for the pre-earthquake. And here, clearly, we have many observations that confirm that it's a linear trend in this semi-log. So again, there is an exponential recovery. And we go back to the pre-earthquake rate in about 4 years. And then it seems we stay, again, close of the pre-earthquake rate. And so in all cases, we have also other example of this. We have a strong increase and then an exponential recovery that lasts between 1 year to 4 years. And it's clearly independent of rain or aftershock. So the most simple explanation is that it's subsurface weakening. And if it's subsurface weakening, it could be different processes, but it should produce a change in the shear wave velocity of the subsurface. And so we have started to investigate that with ambient noise techniques. So you observe the noise at a station and its echo, and you can deduce locally what is the velocity in the subsurface in the first few hundred meters. And if this is an example of a station near the Chichi epicenter, and this is a catchment where I map most of the landslide. And clearly, you see that you have some seasonal cycle and then a large drop, a large decrease of the velocity of the shear waves, and then again an exponential recovery. And the seismic recovery time, strikingly, appears really close of what we observe for the landslide rate. So here it's about also 3-4 years. And so here I show some compilation of some observation from seismic and landslide. There are not many landslide observations, but in 3 events, so for 2 Japanese earthquakes and the Chichi earthquake, we find overlapping recovering time. So it might indicate it's the same processes that is playing there. So in conclusion, so we have been developing a new physically based model to try to predict the total landslide volume and so the erosion associated with earthquakes. And we accounted so for the seismic energy and also wave attenuation, and we showed that you also need to account for landscape steepness, that is quite intuitive. So we predicted rather well about 70% of the event within a factor of 2. And the outlier seems to relate to significant rock strength difference, so it's a future research challenge. But this type of prediction could have many applications in terms of integrating them in landscape evolution models or for natural hazard prediction. And for the temporal relationship between earthquake and erosion, so we could see that there is a post-seismic elevated landslide rate after 4 earthquakes that we have studied. So it seems to be a general mechanism. And that it's clearly independent of forcing, climatic or other type of forcing, and it's probably a subsurface weakening. And that there is hope that this could be associated to observation from ambient noise, from seismic ambient noise. So it would be a way to have a continuous and passive monitoring of the landslide risk in earthquakes areas. Thank you for your attention.
Marc, any question? Any question?
Yeah. Hello.
Yeah.
I'm surprised that you're not considering the focal mechanism for 2 reasons. First, for co-seismic, I would expect that the seismic waves are not going to excite the same landslides depending on the focal mechanisms, and so that's the first reason. I mean, depending on the incidence of the shear waves, it's not going to excite the same landslides. Mm-hmm. And for the post-seismic, because it should control the vertical advection of mass, and maybe I would expect this to also control the amount of material that you would remove on the longer term.
Mm-hmm. Yeah, so for the post-seismic, we cannot control for it because it's 4 thrust. The 4 events are thrust, so we have no data about strike slip or normal fault. So we don't know. For the co-seismic terms, so I quite didn't show it, but here in this database there are every type of earthquakes. It's mostly thrust, but there is about a quarter of normal, a quarter of strike slip, and half of thrust. But we could include in the wave amplitude term, we can make the difference between the different type of earthquakes. It's the only place where it should play. But from the engineering seismology, they observe that there is no main difference in the ground shaking between strike slip and thrust. So you might have some amplification in the hanging wall that we don't consider. But away from that, they don't see difference. And for the normal fault, they observe something like 30% less shaking that we could account for here just by using a slightly different scaling. But it wouldn't make a really big difference. And at the end, in the residual here I don't show the earthquakes per mechanism, but there is no clear trend between the different type of earthquakes.
Yeah, very interesting. I understand, let's say, that the prime focus has been on thrust-related earthquakes, but you also mentioned that some of them have another component. Mm-hmm. This is very much for individual earthquakes. Do you see a chance to generalize it to go, let's say, to a regional scale and to get a kind of quantitative picture over longer time intervals for a larger area?
Well, so I mean, here we try to have a process law, and so you see in the moment magnitude goes to something like 10 power 21 or whatever. The largest are the Denali and the Sichuan earthquake that are almost magnitude 8, and the smaller are magnitude 5 earthquake. So then when you have this, given that there is this caveat at the lithological possible difference, you can then just integrate and you say, if you have an area and you know what have been the past seismicity, you can estimate for scenarios how much landslide were produced each time. I mean, I had to go fast, but we also do some prediction about the area covered and about what extent should be covered by the landslide, so how far they should happen, at least for most of them. So yeah, it could be easily, and this is something we are working on, integrated into a more landscape evolution model, or from a mountain building point of view, what happens when you sum earthquakes, and what happens when it's really deep structure, they will produce landslide. When it's emerging topography, at the start you have no slope, so you start with almost no landslide. So there are a lot of hysteresis and other factors that could play, but they are all prescribed in this, or most of them are prescribed in this equation.